So this is critical equation. Is the screen visible?
Yes, sir.
In the previous class, we have discussed two group diffusion equation to obtain criticality condition. And neutrons born in fission have high energy, and these are slowed down in thermal reactors. A plot of Fermi age model of slowing down of neutrons from mega electron volt range to thermal range. So thermal range is around 0.0253 electron volt, and it is a function of slowing down time small t, and it is shown in the screen. So 1 electron volt is around 11000 Kelvin or 11600 Kelvin. So one group, two group, and multi group, and also Fermi age diffusion methods are shown in the graph. And you can see that Fermi age diffusion is a decreasing, has a decreasing trend, whereas you have a step function like multi-group graph. And you can see that Fermi age diffusion and your J in the graph. So one group is shown in the figure as well as two group and multi group. So in x-axis you have logarithm e, ln e, and in the y-axis you have ln e or logarithm e, or in the x-axis you have t. So t is the slowing down time, and your in the screen you can see the slowing down of neutrons. Ln E dash by E is equal to J, and the E dash minus D in the picture. For critical equation, your small k is equal to k infinite p is nothing but 1. The calculation of leakage factor, capital P, in terms of the physical or nuclear properties of the fuel moderator system is complex for neutrons with a wide range of energies. However, by adopting some approximate methods, the calculation of criticality condition for a reactor in steady state becomes easier and reasonably accurate. So, the commonly employed approximation methods are one group diffusion method, two group diffusion method, modified one group diffusion method, Fermi age diffusion method. So in one group diffusion method, you assume that all neutrons are having same energy, monoenergetic neutrons. In the true group diffusion method, you assume that neutrons are either fast or thermal, where the energy change occurs at one collision, and allowance is made for resonance absorption of neutrons. This approximation is applicable to thermal reactors. So in thermal reactors, you have two types of neutrons. One is fast neutron and another is thermal neutron. So this is called two group, and the method is known as two group diffusion method. In the modified one group diffusion method, the slowing down of fast neutrons, you can account for the slowing down of fast neutrons into the thermal energy range. And in the Fermi age diffusion method, which is shown in the graph, you can see in the upper part of the graph, this employs the continuous slowing down model of Fermi age diffusion method. So you can now expect one group critical equations from steady state diffusion equation. So the source neutron capital S arising from fission, you have the equation D del square phi is equal to sigma A phi plus S is equal to 0. So your S follows from the definition of multiplication factor K infinite for the given absorption neutrons sigma A phi. So your S or source of neutron is equal to K infinite sigma A phi. So now by substituting this S in the original equation, D del square phi minus sigma A phi plus S is equal to 0, you can have the modified expression as D del square phi minus sigma A phi plus K infinite sigma A phi is equal to 0. So you can divide D throughout and rearrange the terms. And the modified term will be del square phi plus K infinite minus 1 sigma A by capital D phi is equal to 0. And this relation can be rewritten as del square phi plus K infinite minus 1 by L square phi is equal to 0, where L square is equal to D by sigma A, and it is the square of diffusion length. Okay. So one group diffusion equation is in the form of wave equation. So your wave equation, is having the form del square phi plus omega square phi is equal to 0. So for neutrons, it is modified as del square phi plus b square phi is equal to 0. So where b square is the bucking and having unit meter inverse, and is a measure of bending or buckling of spatial distribution of neutron flux. And your wave equation, your omega is the frequency. So frequency is replaced by your bucking. This name comes from the similarity of the reactor equation to that of a loaded column. So the geometrical size of the reactor increases, B square decreases. By comparing on these two equations, we can write B square is equal to K infinite minus 1 by L square. Or you can write K infinite by 1 plus L square B square is equal to 1. So this is the one group critical equation where K plus K infinite P is equal to 1. For criticality, one group non-leakage probability P can therefore be identified as P is equal to 1 plus P is equal to 1 by 1 plus L square B square. So you have the modified one group diffusion theory by a method. In a thermal reactor, neutrons of all energies exist and neutron cross section vary greatly with energy. However, for a large thermal reactor, it is possible to modify the two group criticality equation. So you can write K infinite by 1 plus L1 square Bg square multiplied by 1 plus L2 square Bg square is equal to 1. So your PF is equal to 1 by 1 plus L1 square Bg square, and your PT is equal to 1 by 1 plus L2 square Bg square. And your K infinite is equal to eta F P epsilon. So you can expand it as k infinite by 1 plus L1 square Bg square plus L2 square Bg square plus L1 square L2 square Bg to the power 4 is equal to 1. So for small values of Bg square, you can neglect the term Bg to the power 4 L1 square L2 square, and the criticality condition will be k infinite by 1 plus L1 square plus L2 square Bg square is equal to 1, and your k infinite by 1 plus m square Bg square is equal to 1, where m is the migration area and is nothing but L1 square plus L2 square. The migration length m is equal to 1/6 of the distance traveled by a neutron from the moment it is born in fission to the moment it is absorbed. So for some common moderators and reactor types, the migration length along with other diffusion parameters can be placed in a tabular form. So for water H2O, your diffusion length is 2.7 centimeter. The slowing down length is 5.2 centimeter. The migration length is 5.9 centimeter. For heavy water D2O, your diffusion length is very large, 100 centimeter. The slowing down length is 11.4 and your migration length is 101. For beryllium moderator, your diffusion length is 21 centimeter. The slowing down length is 10 centimeter and your migration length is 23.3 centimeter. For carbon, your diffusion length is 54 centimeter. The slowing down length is 19.2 centimeter and the migration length is 57.5 centimeter. So for PWR type reactor, your diffusion length is 1.8, slowing down length is 6.3, and migration length is 6.6. For BWR type reactor, your diffusion length is 2.2, slowing down length is 7.1, and migration length is 7.3. Your HTGR type of reactor, diffusion length is 12, slowing down length is 17.3, and your migration length is 21 centimeter. So, modified one group critical equation has the same form as that of one group or one speed critical equation. If we replace L square by M square, we get the modified one group diffusion equation. In your one group diffusion equation, there is L square term, and in modified one group diffusion equation, you have M square term, where M is your migration length. So del square phi plus k infinite minus 1 by m square phi is equal to 0. So the spatial variation of neutron flux according to one group model and the modified one group model is similar. However, for modified one group case, Bm square is defined as Bm square is equal to k infinite minus 1 by m square. We now generalize the discussion to apply Fermi age theory. But before that, let us have some discussion. Suppose you compare one group critical equation and modified one group critical equation. So how can you compare it? There is a m term in a modified one instead of L term in a one group critical equation. The next part of the discussion is Fermi age theory, or this is to explain Fermi age diffusion, which has a decaying trend as you see in the graph. ln decreases as your T increases. So fast neutrons can be divided into a large number of groups, say capital G, of decreasing energy. If we assume that all neutrons in a group slow down into the next group of lower energy and fission is induced by thermal neutrons only, then a natural extension of two group critical equation will be eta FP epsilon by 1 plus L thermal square Bg square pi I from 1 to G 1 plus Li square Bg square is equal to 1. So in graph, you can have your G in x-axis and N in y-axis, and you can have these transitions. where total resonance escape probability P is given by your P is equal to I to G Pi, summation I to G Pi, where Pi is the resonance escape probability for the ith group, and your Pi is equal to summation K is greater than I, Gik sigma Ri. Similarly, Li is equal to Di by sigma Ri is diffusion length or slowing down length for the ith group. For a large number of fast neutron groups, slowing down from one group to the lower energy group is physically equivalent to continuous slowing down model. With such assumption, you can write limit g tends to infinite, summation I is equal to 1 to g, Li square is equal to tau, where tau is the Fermi age of thermal neutrons. So, we can have a more convenient form in a logarithmic expression. So your ln k infinite is equal to ln 1 plus L thermal square Bg square plus summation I is equal to 1 to G ln 1 plus Li square Bg square. Here your k infinite is equal to eta f p epsilon. As G tends to infinite, Li square becomes extremely small, and since Bg square is usually small, you can take ln 1 plus Li square Bg square is nearly equal to Li square Bg square. So by using this result, you can get ln k infinite is equal to ln 1 plus L thermal square Bg square plus Bg square summation I is equal to 1 to G Li square. So ln 1 plus L thermal square Bg square is equal plus Bg square tau. So you can have your ln k infinite exponential minus tau Bg square by 1 plus L thermal square Bg square is equal to 1. So you can take the antilog and obtain k infinite exponential minus tau Bg square by 1 plus L thermal square Bg square is equal to 1. And this is referred to as Fermi age critical equation for a Bayer reactor. It is based on continuous slowing down model. The expression exponential minus Bg square tau represents the non-leakage probability for fast neutrons while they are slowing down. Unlike the 1 and 2 group critical equation, the Fermi age critical equation is transcendental in nature and has to be solved numerically. So what are the practical applications? For practical applications of Fermi age critical equation, we have to simplify the equation k infinite exponential minus tau Bg square by 1 plus L thermal square Bg square is equal to 1. And for small values of Bg square, that is for large assemblies, we have your exponential minus Bg square tau is nearly equal to 1 minus Bg square tau is equal to 1 plus Bg square tau inverse. Using this result, in the expression k infinite exponential minus tau Bg square by 1 plus L thermal square Bg square is equal to 1, you can have k infinite by 1 plus L thermal square Bg square multiplied by 1 plus Bg square tau is equal to 1. And it is analogous to 2 group critical equation if we identify Li square as tau. Again, on multiplying the denominator and neglecting terms in Bg to the power 4th, we can rewrite it as modified 1 group critical equation. And it is nothing but k infinite by 1 plus L thermal square plus tau Bg square is equal to 1. Or you can write k infinite by 1 plus m square mg square, k infinite by 1 plus m square Bg square is equal to 1, where m square is equal to L thermal square plus tau, and it is m square is nothing but migration area for thermal neutrons. So for different reactor shapes, buckling, asymptotic flux and minimum critical volume can be expressed in a tabular form. For infinite slab, your buckling Bg square is equal to pi a square. Asymptotic flux distribution is phi 0 cos pi x by a. For a spherical geometry, your buckling Bg square is equal to pi by r square. Asymptotic flux distribution is phi 0 by r sin pi r by a. and your minimum critical volume Vc is around 130 by b square. For rectangular parallelepiped, your buckling Bg square is equal to pi by a square plus pi by b square plus pi by c square. And your asymptotic flux distribution will be phi 0 cosine of pi x by a cos pi y by b cos pi z by c. And your minimum critical volume Vc will be 161 by b cube, where a is equal to b is equal to c. For a finite cylinder, your buckling Bg square is equal to 2.405 by r square plus pi by h square. And your asymptotic flux distribution will be phi 0 j0 2.405 by r multiplied by small r cosine of pi z by capital H. And your minimum critical volume Vc will be 148 by b cube, for h is equal to 1.847 r. So let us have an example. The infinite multiplication factor for VWR core of extrapolated diameter 4.4 meter and height 3.6 meter is 1.2. Okay. So you can calculate the effective multiplication factor by using I modified one group, double I, two group, double three, forming a critical equation. So it is given that Bg square is equal to 2.405 by r0 square plus pi by 2h square. Okay, for an finite cylinder. For the finite cylinder, your buckling is equal to 2.045 by r square plus pi by h square. So here r0 is equal to how much? R0 is equal to 2.2 because diameter is 4.4 meter. And your h is equal to how much? 2h is equal to 3.6. So your Bg square will be 2.405 by 2.2 square plus pi by 3.6 square. So this is nothing but 1.96 meter to the power minus 2, which is nothing but 1.96 into 10 to the power minus 4 centimeter to the power minus 2. What is m square? Look, the formula for m square is m is equal to m for PWR is equal to 6.6, BWR is equal to 7.3, and HTGR is equal to 21. So your here this is a BWR type. So your m square is equal to 7.3 square. 7.3 square is equal to 53.29 centimeter square. And your L square is equal to 4.84 centimeter square, because the formula for L is equal to how much? This is given here in the table 16.1. 1.8 square is equal to 4.84 centimeter square. For modified one group theory, your K effective will be K infinite by 1 plus m square Bg square is equal to 1.2 by 1 plus 53.29 multiplied by 1.96 multiplied by 10 to the power minus 4 is equal to 1.188. This is for one group. For two group, your K effective will be 1.2 by 1 plus 1 plus 4.84 multiplied by 1.96 multiplied by 10 to the power minus 4 whole multiplied by 1 plus 50 multiplied by 1.96 multiplied by 10 to the power minus 4. This is from the equation K effective will be K infinite by 1 plus L thermal square Bg square multiplied by 1 plus tau Bg square. So now it will be 1.2 by 1.0009 multiplied by 1.0098 is equal to 1.187. So for Fermi age theory, your K effective will be K infinite exponential minus tau Bg square divided by 1 plus L thermal Bg square. So this is nothing but 1.2 exponential minus 50 multiplied by 1.96 multiplied by 10 to the minus 4 divided by 1.0039, which is equal to 1.2 exponential minus 0.0098 by 1.0009 is equal to 1.187. So the two group and Fermi's theory yield the same value for K effective. It is for two group it is 1.187, for Fermi's it is 1.187. Then properties of a critical system with and without a reflector. So due to the finite size of reactor, neutrons leak out while slowing down and diffusing as thermal neutron in the moderator. That is, these neutrons are lost from the system in a due course of time. However, the purpose of reflector is to scatter leaking neutrons back into the core. This design feature reduces the leakage and hence critical size of the reactor and critical mass of fissile material apart from the cost of the system, and increasing safety of the public from leaking radiation. It increases the average power output, which is proportional to the average thermal neutron flux. The properties of reflectors are determined by leaking neutrons, which are epithermal. These neutrons are returned back to the core as thermalized neutron. The reflector is therefore expected to have properties similar to a moderator, that is, high sigma s, low sigma a, and low L. However, diffusion constant D of reflector medium should be small so as to increase the probability of neutrons returning to the core. So, neutrons having energy more than thermal neutron but less than resonance neutron are referred as to epithermal neutron. And you can have comparison of neutron flux distribution in a reactor with or without a reflector, and it is shown in the screen. The solid line is for bare one and the dotted line is for reflected one. So, you know d del square phi minus sigma f phi plus k infinite sigma f phi is equal to 0. So, your del square phi plus b square phi is equal to 0, and your b square is equal to k infinite minus 1 by L square. In modified one group model for thermal reactor, this relation modifies to b square is equal to k infinite minus 1 by m. The corresponding steady state diffusion equation for reflector R is given by dr del square phi r minus sigma r phi r is equal to 0. So, your del square phi r plus kr square phi is equal to 0. So, your kr square is equal to sigma r by dr is equal to 1 by lr square. So, here there is no source term. The influence of the reflector on the reduction of the critical size of the core is evaluated by solving the diffusion and buckling equation for the reactor core and the reflector. So, in this analysis, you have to use continuity condition or neutron flux and current at the interface between core and reflector. This means that here we replace the vacuum condition considered for the bare core solution. However, an approximate method can be introduced in terms of the reflector saving delta, which is a measure of decrease in critical size of the reactor due to presence of reflector. For a few typical reactor type, reflector saving are given below. Okay. So, suppose we consider a infinite plane slab, an infinite bare plane reactor. So, here H0 is the critical size of the bare reactor and H is the size of the reflected reactor. And your delta is equal to half H0 minus half H. For a spherical geometry, R0 is the critical size of the bare reactor and capital R is the size of the reflected reactor. So, your radius of core is capital R and your delta is equal to R0 minus R. So, with this methodology, for either a small reflector thickness T where delta is small or a large reactor core where H and R are large, your T is very greater than LF, then delta or thick reflector is equal to D by dr LR. And for T is very smaller than LR, your delta, that is for thin reflector, d by dr t, and your Lr square is equal to dr by sigma r. So your d is equal to dr if the moderator and reflector are of the same material and the properties of fuel in the core is not large. The one group method shows that a reflector thickness T of 1.5 to 2 m is virtually equivalent to an infinite reflector as far as the effect on critical mass is concerned. So look, in one group theory, the critical size is reduced of an infinite plane slab reactor as a function of reflector thickness. So H decreases and delta increases for infinitely thick reflector. Okay. So let us have another example. In one group method, neutrons slow down to thermal energies and energy distribution of these neutrons is given by Maxwell function. So you know, in Maxwellian form, your n, which is a function of E, is 2 pi n by pi k t to the power 3 by 2 e to the power half exponential minus e by kt. And your NED is the number of neutrons per centimeter cube with energies between E to E plus del E. And N is nothing but the total neutron density or neutrons per centimeter cube. So the energy dependent flux for thermal neutrons is given by phi is equal to N multiplied by V. So this is nothing but 2 pi N by pi kt to the power 3 by 2 multiplied by 2 by m to the power half exponential minus e by kt. So we have used the relation between speed and energy here, and your V is equal to 2e by m root over of 2e by m, where m is the Newton mass. So one group thermal flux phi t is then given by phi t is equal to integration over t phi d. So your t on the integral signifies that the integration is to be carried out over the thermal energies, which are normally taken to extend up to your 1.01 eV is equal to 5 kT. Since the exponential term in phi drops to such small values above this energy that very little error is made by carrying out the integral to infinite. So your phi t is equal to 2 pi n by pi kt to the power 3 by 2 multiplied by 2 by m to the power half integration 0 to infinite exponential minus e by kt d. This is nothing but 2n by root over pi 2 kt by m root over of half, or root over 2 kt by m to the power half. So phi t is equal to 2n by root over of pi multiplied by root over of 2 kt by m. So your first step is to determine the dimension of critical system for a cylinder. So your Bg square is equal to 2.405 by r square plus pi by h square. So your h by 2r is equal to 1.2. So h will be 2.4r. So your Bg square is equal to 2.405 by r square plus pi by 2.4r square is equal to 7.5 by r square. For a critical reactor, Bg square is equal to Bm square is equal to 8.6 meter inverse, meter to the power minus 2. Hence, the square of the critical dimension is obtained from Rc square is equal to 7.5 by 8.6 is equal to 0.87 meter square. So that Rc is equal to 0.93 meter and your Sc is equal to 2.23 meter. So the fuel rods are arranged in a square lattice with a pitch of 0.152 meter. Hence, the effective area per rod is 0.152 square is equal to 0.0231 meter square. The cross-sectional area of the core is pi RC square is equal to 3.14 multiplied by 0.93 square is equal to 2.72 meter square. Number of fuel rods are 2.72 by 0.0231 is equal to 117. Since each of these rods has a diameter of 25.4 millimeter, which is equal to 2.54 into 10 to the power minus 2 meter, and the length of core is that is 2.2 meter, the volume of 117 rod is uh, equal to the total volume of the fuel, that is equal to 1.4 multiplied by pi multiplied by 2.54 multiplied by 10 to the power minus 2 square multiplied by 2.23 multiplied by 117, which is equal to 0.132 meter square. So the density of uranium metal is 19.0 multiplied by 10 to the power 3 kg per meter cube. So the total mass of uranium fuel for bare reactor is 0.132 multiplied by 19.0 multiplied by 10 to the power 3 is equal to 2.51 into 10 to the power 3 kg. So your RS square is equal to integration R square Q dV by Q dV, where Q is a function of R and it is the slowing down density. So the solution of the Fermi's equation for slowing down density Q, which is a function of R and tau for a point source, is Q is equal to S e to the power minus R square by pi divided by 4 pi R to the power 3 by 2. So your dV is equal to 4 pi R square dr for spherical geometry. So you can write Rs square is equal to 4 pi S by 4 pi tau to the power 3 by 2 integration 0 to infinite R to the power 4 e to the power minus R square by 4 tau d tau divided by 4 pi S by 4 pi tau to the power 3 by 2 integration 0 to infinite R square e to the power minus R square by 4 tau d tau, which is equal to 3 root over pi by 8 multiplied by 4 tau to the power 7 by 2 divided by root over pi by 4 tau to the power 5 by 3 is equal to 6 tau. And your tau will be 1 by 6 Rs square. So your phi t is equal to 2 by root over pi n v t. So your phi 0 is equal to n v 0. Your phi 0 by phi t is equal to root over pi by 2 v 0 by v t. So your Vt is equal to 1.284 t to the power half multiplied by 10 to the power 4 centimeter per second. And your V0 is equal to 1.284 T0 to the power half multiplied by 10 to the power 4 centimeter per second. So your T0 is equal to 293.61 Kelvin. So your phi 0 by phi t is equal to root over pi by 2 T0 by t to the power half. Okay. So in the next class we shall have the next part of the discussion, and if you have any doubt also you can ask in the next class.
धन्यवाद.
Thank you.
Thank you, sir.
Okay.